semester 1. The paper code is MACC2102. So now let's start the concept of prime number. So first we will define the definition of prime number. Prime number. So what is the definition? An integer p, this is greater than 1, is called a prime number. Is called a prime number if its only positive divisors are divisors are 1 and p. Okay, so now if we think about the example, before that, if someone asks you the question, is the number 1 prime? Is the number 1 prime? So the answer is simply no, it is not prime. Obviously, it is divisible by 1 only, but it is not prime, as 1 is not greater than 1. Because in the definition, it is said the prime number must be greater than 1. So now we come to the example of prime number. So the example is 2, 3, 5, 7, 11, 13, 17, 19 and so on. Here you just observe these are positive integers greater than 1, and it is only this number is divisible by 1 and itself. So that's why all these number are prime number. So here important note, say let Pi denote the ith prime number. So then our P1 will be 2, P2 will be 3, P3 will be 5, and P4 will be 7, and so on. Now someone asked you to give an example of a composite even prime number. So next question, give an example of a prime which is even. So obviously your example will be 2. So 2 is the only prime which is even number, and all other prime will be odd. So here our important note is, note again, 2 is the only even prime. So that means if P is greater than 2, if P is a prime and it is greater than 2 prime number, then P must be odd. The prime must be odd number or odd integer or positive integer. So every prime greater than 2 must be an odd prime. So now the question is, so what should be the number of primes? Next question, question 3. So the number of prime numbers, it is finite or infinite. So the number of prime numbers is always infinite. So we'll see one important theorem. There are infinitely many primes. There are infinitely many primes. Many primes. So this theorem says us the number of prime is always infinite. So again we come to note, let S be the set of all natural numbers such that P is prime, set of all positive integers such that this is basically set of all primes. Set of all primes. So obviously then the cardinality of S, that is infinite. Okay, and here we will do one important theorem, and before that we will do one more definition. This is definition of composite number. Composite number. So if a number P is not prime, then that number is called composite number. So a number, or the number means integer, say n, this is greater than 1, is called composite, number if it is not prime. If it is not a prime. Okay, so that means n can be expressed as n1 into n2, where 1 less than n1 less than n and 1 less than n2 less than n. As for example, 4 is a composite number, we can write 2 into 2. 6 is composite number, we can write 2 into 3, where you will see 1 less than 2 less than 6, 1 less than 3 less than 6, and here 1 less than 2 less than 4. So that's why 4, 6, 8, 9, this number is composite. 3 into 3. So this are the composite number. Now we come to some important theorem. The theorem is, say, if, or you can say the important question. The question is like this: if A is prime to B, question, or you can say the theorem, if A is prime to B and B is prime to and A is prime to C, and also A is prime to C, then A is prime to BC. That we have done in previous class. Now we will solve some problem. So problem number 5. What is the problem? If A and B belongs to Z plus, that means both are positive integer with GCD of AB equals to 1. So GCD of AB equals to 1, that means is prime to B, that means they are relatively prime. Then prove that GCD of A plus B, A minus B, that will be 1 or 2. Now how to solve this kind of problem? So in previous class, we recall some basic facts. The A is prime to B if and only if GCD of AB equals, this is the definition of relatively prime or co-prime. That means there exists integer unique int AUV belongs to Z such that AU plus BV equals to 1. That we have done in previous class. Now we come to the question, what is exactly given? So here given A and B both are positive integers. So Z plus means set of all positive integers, that means set of all natural numbers. It also given they are relatively prime, that means GCD of AB equals to 1. So what we have to prove? We have to prove that GCD of A plus B comma A minus B, this is either 1 or 2. That we have to prove. Now question is how to prove. Okay, so let D equals to GCD of A plus B and A minus B. Since D is the GCD, so then we can write D divides A plus B and also D divides A minus B. Okay, this is the definition of the greatest common divisor. From that we can write D divides A plus B into X plus A minus B into Y for all XY belongs to Z. Okay, this is one. Now if we take, this is holds for all XY belongs to Z. So take X equals to 1 and Y equals to 1. In that case, D divides A plus B into 1 plus A minus B into 1. And that implies D divides 2A. Okay. Similarly, if we take in particular X equals to 1 and Y equals to minus 1, so D divides A plus B into 1 plus A minus B into minus 1. That means D divides 2B. Okay, so from 1 and 2 and 3, what we can say? Therefore, from 2 and 3, we say that D divides GCD of 2A 2B, because D divides 2A, D divides 2B, so D divides GCD of 2A 2B. That means D divides 2 into GCD of AB, and it is given GCD of AB equals to 1, so D divides 2. Since GCD of, they are co-prime, relatively prime to each other, so D divides 2. That means D will be either 1 or 2, because the greatest common divisor always non-negative. It will be not minus 1 minus 2, it will be 1 or 2. So that means we proved that GCD of A plus B, A minus B, that was exactly D. This is 1 or 2. So hence it is proved. Now we come to next important problem. So this is problem number 7. Very, very important. If A is prime to B, if A is prime to B, prove that A plus B is prime to A. So what is exactly given? So it is given that GCD of AB equals to 1, because A is prime to B. Since it is given A is prime to B, that means GCD of AB equals to 1. What we have to show that? We have to show that A plus B is prime to AB. That is, we have to show that GCD of A plus B and AB equals to 1. Okay. So start now. A is prime to B, and that implies GCD of AB equals to 1. So this is 1. So that means there exists integer u and v such that AU plus BV equals to 1. So this is we are considering is at 1. So from 1, what we get? So therefore from 1 we get A plus B into V plus A into U minus V, that will be 1. So BV, AV and AV, that is cancel out, so it will be AU plus BV, because since A plus B into V plus A into U minus V, that is equals to AU plus BV. So that means here, since UV are integer, so we can write GCD of A plus B comma A is 1. Since U and U minus V and V all are integer. Again from 1 we get, again from 1 we can write, or we get A plus B into U plus B into V minus U. This is equals to 1. Why? Because A plus B into U plus B into V minus U. So that will be AU plus BV. And this implies GCD of A plus B comma B, it will be 1. Why? Since U and V minus U both are integer. So that means here A plus B is prime to B. So from here we can write A plus B is prime to A. And from here we can write A plus B is prime to B. So this is our 2 and this is our 3. Now what we will see in the theorem? Theorem, if A is prime to B and is prime to C, then A is prime to B.Sc. So by using this theorem, here A plus B is prime to A and A plus B is prime to B, that means A plus B is prime to AB. Since GCD of AB equals to 1, since therefore by 2 and 3 we conclude that A plus B is prime to AB. Okay. Here we use this recall. What is the recall here? We recall the basic facts. So fact is, if X is prime to Y and X is prime to Z, that implies X is prime to YZ. So we proved this problem. Now we come to next question. This is question number 8. If A is prime to B, if A is prime to B, then prove that the square is prime to B. The square is prime to B, and also we can prove a square is prime to B square. The square is prime to B square. How we will prove this problem? Okay, we come to the solution. Since A is prime to B, so GCD of AB, that will be 1. That means there exists integer UV belongs to Z such that AU plus BV equals to 1. So, star marks. Now start from 1. We have to show A square is prime to B square. Here we have to prove that A square is prime to B. That we have to prove. So now from star, what we get? AU plus BV equals to 1. And from that we can write AU equals to 1 minus BV. So just squaring on the both sides. So that will be A square U square equals to 1 minus 2BV plus V square V square. And that also we can write A square U square plus B into 2V minus BV square. This is equals to 1. And that implies GCD of A square comma B equals to 1. Why? Since U square and 2B minus U square belongs to Z and 2B minus BV square, that is also Z. Okay, and what we have seen here, we have seen the result is if there exists UV belongs to Z such that UV plus BB, from that we can write GCD of AB equals to 1. So that means here we can write GCD of square B equals to 1. And that implies A square is prime to B. Now we come to the second problem. Okay, so in the first case, what we have proved, okay, so here we will use the fact. The fact is that we have shown in the first portion, first part, the GCD of AB, that if A is prime to B, that implies GCD of A square B equals to 1. Okay, so we'll use this fact. Now, GCD of AB equals to 1, that implies GCD of A square B equals to 1. This is basically by the first problem, by 1. And from that we can write there exist integers, say m comma n belongs to Z such that A square into m plus b into n, this is equals to 1. Now, from that we can write bn equals to 1 minus A square m. And we are squaring on the both sides. So that means bn square equals to 1 minus square n whole square. That means b square n square equals to 1 minus 2 square m plus a to the power 4 m square. That implies n square into b square plus, that implies square into square into 2m minus square m square plus b square into n square, this will be 1. So that implies GCD of a square comma b square equals to 1. Why? Since 2m minus a square m square, this is integer and n square is also integer. So that means a square is prime to b square. And that implies a square is prime to b square. So again we have proved the second part of the question. Now we come to the next important question. This question is very, very important for Calcutta University or any other university examination. This is question number 9. If GCD of AB equals to 1, then prove that GCD of A plus B comma A square minus AB plus B square, this will be 1 or 3. The thing is how to prove, how to solve this kind of problem. So okay, we will come to the solution. What is exactly given? So it is given that GCD of AB equals to 1. What we have to prove? We have to prove that GCD of A plus B comma square minus AB plus B square, this will be 1 or 3. Okay. So now what we have shown, just say now what we know, GCD of, if A is prime to B, that means GCD of AB equals to 1. That implies GCD of A plus B comma AB equals to 1. That means A plus B is prime to AB. That we have proved earlier in this problem. If A is prime to B, then A plus B is prime to AB. That means if GCD of AB equals to 1, GCD of A plus B comma A plus B equals to 1. Okay, so now let D equals to GCD of A plus, that we have to calculate, A square minus AB plus B square. And from that we can write then D must divides A plus B, and also D divides square minus AB plus B square. And that implies D divides A plus B into X plus square minus AB plus B square into Y for all X comma Y belongs to Z. Okay. So here if we take X equals to A plus B and Y equals to minus 1, what we get? Because this is holds for all integers, it obviously holds for X equals to A plus B and Y equals to minus 1. So we get D divides A plus B into A plus B plus A square minus AB plus B square into minus 1. That implies D divides 3AB. So what we get here, so therefore, here you have seen D divides A plus B, D divides A plus B and D divides 3AB. Okay, so that implies, this two case implies D divides 3. Why? Because since GCD of A plus B and AB, this is equals to 1. So since D divides 3, that means D is either 1 or 3. And you know greatest common divisor always non-negative. So what is our D? So D was basically GCD of this element. So therefore in position of D you can write GCD of A plus B and A square minus AB plus B square. This will be either 1 or 3. Okay. So now we will come to the next question. This is question number 10. That question also important. The question is prove that the product of three consecutive integers of any three consecutive integers is divisible by 6. Is divisible by 6. Okay. So now we come to the solution. So by division algorithm, what we can say? Any integers upon division by 4 by 3 leaves one of the remainder, one of the remainder 0 or 1 or 2. So any integer of the form, so either it will be 3k or it will be 3k plus 1 or it will be 3k plus 2. Now when n equals to 3k, then n is divisible by 3. Then n is divisible by 3. And when n equals to 3k plus 1, then n plus 2. That means 3k plus 1 plus 2. So it will be 3 into k plus 1. And that will be which is divisible by 3. And when n equals to 3k plus 2, then n plus 1, that will be 3k plus 2 plus 1. That means 3 into k plus 1. So that will be divisible by 3. So that means if any case, so that means it follows that for any integer n, n, 3 must divides either n or n plus 1 or n plus 2. So that means 3 must divides the product of 3 consecutive integers. Okay. So this is our one. Now product of again product of any 3 consecutive integers, product of any 2 consecutive integers is divisible by 2 also. That means if n into n plus 1, this is divisible by 2. So 2 divides this. And from that we can write 2 must divides n into n plus 1 into n plus 2. So this is 2. Now since from 1 and 2 what we have seen, we have Therefore, from 1 and 2 we have 2 divides n into n plus 1 into n plus 2, and also 3 divides n into n plus 1 into n plus 2. That implies 2 into 3, that means 6 divides n into n plus 1 into n plus 2. Why? Because since GCD of 2 and 3 equals to 1, and that implies product of any 3 consecutive integers is always divisible by 6. Okay, now we come to next important problem, problem number 11. This problem is important for Calcutta University examination. If P be a prime number, if P be a prime number and 1 less equals to A less than P, then prove that P is prime to A. Then prove that P is prime to A. That means GCD of AP equals to 1. So that is GCD of AP, that will be 1. So we'll come to the solution or proof. What is given here? Given P is a prime, and also it is given 1 less than equals to A less than P. What we have to show? We have to show that P is prime to A. P is prime to A. That means GCD of AP equals to 1. Okay, so that is, we have to show GCD of AP, this will be 1. So now we consider D equals to GCD of AP. Then from that we can write D divides A and D divides P. Now since P is prime and D divides P, since P is prime, this is given, and D is a divisor of P, so that implies the possibility of D is either 1 or P. But what we have seen, but here it is given A is less than P and D divides A. So from that case, D equals to P is not possible. So we must have here D equals to 1. As in that case, D equals to P is not possible because D divides A and A less than P. Not possible. So D must be equals to 1. So D is basically GCD of AP. So what we have proved, GCD of AP equals to 1. So this is basically for 2 marks question. Okay. So next question is question number 12. And this question is also important for Calcutta University examination. Prove that for n greater than 3, the integer n plus 2, the integer n plus 2 and n plus 4 n plus 4 cannot be all primes. Be all primes. Why here it is taken in greater than 4? Why? Why it is taken? Because if we put say n equals to 3, what will happen? If n equals to 3, say n plus 2 will be 3 plus 2, 5. And n plus 4 will be 3 plus 4, 7. And you will see 3, 5, 7 all are prime. This is only happen for n equals to 3. But if we take n greater than 3, this possibility does not occur. So how to solve this problem? We'll come to the solution here. The solution is, so by division algorithm, if we divide an integer n by 3, what will be the remainder? It will be 0 or 1 or 2. Okay, so by division algorithm, any integer division, any integer upon division by 4, division by 3, leaves one of the remainder, either 0 or 1 or 2. So any integer is of the form it may be 3k or 3k plus 1 or 3k plus 2. Now when n equals to 3k, then n is composite number for some k belongs to z. Then n is composite number because it is multiplication of 3 and k. So then n is composite number. Okay, when n equals to 3k plus 1, then n plus 2, that will be 3 into k plus 1, which is also a composite number. Because it is 3 multiple, 3 is an integer greater than 1, k plus 1 is integer. Okay, so this is also a composite number. And when n equals to 3k plus 2, then n plus 1, that will be 3 into k plus 1, and again that will be a composite number, which is also a composite number. Okay, so here n is basically greater than 3, so k be an integer for some k belongs to z, and k will be greater than 1. Okay, so in any case, either n equals to 3k or n equals to 3k plus 1 or 3k plus 2, we have seen, okay, n is a composite. So thus what we conclude, for n greater than 3, the integer either n or n plus 2 or n plus 1 or n plus 4. Okay, that will be n plus 4, and this will be n is 3k plus 2 plus 4, 3k plus 6, or n plus 4 cannot be all primes. And this is only possibility. So you have not only possibilities that three numbers n plus 10 plus will be all prime for n equals to 3 only. Thank you so much.